Hello and welcome back. Okay, so here is the build as it currently stands, and it's time to get things a little bit tidier. Now, all of this up here is the bus control circuitry. So this basically takes control lines from the pipeline that talk in terms of the address of registers, and it converts it into all of the individual control lines that go into the registers here. Now, in a recent mailbag video, I actually showed this PCB. Now this is the bus control circuit, which replaces all of this, and it is designed to sit right in the middle there and provide all the interconnects via nice short links, and this will give me a chunk of desk back. Now the remainder of this video is the design of this board and the soldering of it, and I'm hoping you'll find that interesting, although there's quite a lot of footage there and we don't really build anything fundamentally new to the circuit, so I'll understand if not everybody wants to watch the whole of that. But I do drop a few interesting hints about the way some of these connections are going to go into some new bits of circuitry in the not too distant future. Okay, here we go. Okay, I'm going to start by creating all the inputs and outputs. Okay, so we've got 4 general purpose registers, and they have a 5-pin header. And we need the constant register. Now the constant register board actually just has 3 terminals. We've got assert to main and load from the memory data bus. But on here I'm going to put 4 just to keep the door open for some extensions I'm thinking might be necessary in the future. So that's the assert to the main bus and the load from the memory bus lines. That coupled with ground is the wires that we've currently got on the register. I'm going to add a 4th line for loading from the bus, because the address that I'm going to give this on the bus control, I'm not going to be so pressed for room that I need to overlap different devices with the same address where one only needs a load and one needs an assert. So I'm basically going to wire the same address as what's going to be used for asserting the constant register to the bus to here for the load from the bus, and if we don't use it, we don't use it. Right, now we need the address registers, and they are 8-way headers. Now this is the first one that I've always referred to as the program counter, but I'm going to give it a slightly weird name here, which will all become clear in a few videos' time. Okay, for the clock line we need to give it a distinct name from the clock line that's going to be incoming from the rest of the system, because we need to do some buffering on that. But I have looked at the fan-out limits for the HCT chips, and you can actually take a single TTL signal and go into up to 40 HCT inputs, which means we can just use the one common clock outgoing line to clock all of the address register chips. Now we have to worry about the outputs that we're not actually using yet. Now the transfer register is not going to need the clock or the clear line, nor will it need increment or decrement, but it will want the various load and assert lines from the 16-bit bus. Call it TX. Right, that's convenient. It still fits on an 8-way. Okay, so we've got the load and the two assert lines for the 16-bit portion, and then we've got just load and asserts for the 8-bit portions. Actually, once again, to allow for expansion later on, there is another line I want to add to this. And all will become clear in time. It does mean I need a different header. Okay, we're going to need an output header for memory as well. And once again, this is awkward because I haven't entirely designed the memory subsystem. But we need an assert line for the memory bridge, and that will be a line that when activated will take whatever's on the memory data bus and push it onto the main bus. We need a load line, so this is when we're writing to memory. We also need this direction line. Now this is going to go low at the same time as the load line, but it stays load for the entire cycle, and this means we can avoid any kind of contention on there with at the end of the write portion of the clock cycle. Now the circuitry to drive this is something that we're going to have to build as we go on here. Right, now these two lines I've added here, which are memory request and memory acknowledge, are lines that kind of exist on other processors, and I think I want to be able to implement these because I've got a couple of plans. The memory request line is going to have to be directed over to the pipeline, but the memory acknowledge line is going to come from the bus control. A section of the pipeline in stage 2 which decides at any given point in time what register is asserting to the address bus. And the memory request line is basically going to be a request from another subsystem saying, actually, I want to take over that. And so memory acknowledge is an output from pipeline stage 2 indirectly that says, okay, I'm no longer driving the address bus. You can do what you want to do. Now the way this is going to be implemented, I will cover a bit more when I actually get to putting that circuitry in, but we've got a 3 to 8 line decoder selecting what register should be asserting to the address bus. So the memory acknowledge line is just going to be an otherwise unused line coming out of that decoder, and that's going to be line 0. The address select output from pipeline stage 2, if that goes to 0, then no register is driving the address bus, and this line will go low, and so whatever is waiting on that response will know it can actually drive a value onto the address bus. And then pipeline stage 2, whenever it's outputting 0, will obviously also output a set of combinations to the other things that will affect either the address bus or the data bus coming from memory to make sure nothing is interfering with those signals. Actually, I don't think we need to worry about memory request here because we've not built any of that circuitry, and that doesn't actually come from the bus control circuitry. Right, now we get on to outputs that we don't have a nice clean location to place it, but we definitely need an ALU assert line, but we're going to have an unknown number of additional devices hanging off the bus that we're going to need output wires for, and that's load and assert lines. On the main bus, we've got line 0 is null, 1, 2, 3 and 4 are A, B, C and D respectively. 5 is the constant register, 6 and 7 are TL and TH, 8 is the ALU. Last time we talked about it, we said we were going to make 15 the memory bridge, but then we've still got a number of other lines that we currently haven't allocated. So I'm going to fill in some stubs for those, but we're just going to have to number them. I'm just thinking we're probably going to want clock and reset going into memory. But I'm just going to pass those straight through. No, actually this is the same as the memory request. We'll worry about that later. Okay, so that is all of the outputs. Now we need to worry about all of the inputs. We're going to need to hook these up to a header at some point. We need to select the device that's asserting to the main bus, 4-bit. Then we need to select what device is loading from the bus, also 4 bits. We need 3 bits, which are going to control what register is asserting to the address bus. And then 3 bits to select what is asserting to the transfer bus. Now, if you remember, the transfer bus load, we kind of multiplex that up with the decrement operations. What am I going to call this? And the increments were split into 2 halves. So that's the program counter and return address increment selection lines. And then we've got stack pointer, SI and DI on another pair. Okay, so now we've got the LHS and RHS inputs to the ALU. That's quite a lot of lines. And we're also obviously going to need input lines for power and ground. Now, basically all of these I'm expecting to come from a cluster at the top of the board. There's an awful lot of pins here. This is going to be a pain trying to assemble the circuit board. I wish I knew exactly how many device lines I actually needed. Okay, so I've got 4 8-way inputs and 4 4-way inputs. That means when we come to lay out the PCB, we've got some choice. We could actually go with 4x12 or 6x8. Not looking forward to plugging these in and out though. Actually, let's start looking at laying these out on a PCB, see how they're panning out. Okay, seems to have come out the opposite way. Now, I'm expecting the control board to comfortably just fill the gap between these. So I haven't worked out what the width is, but the height is going to be the same as these 5 register boards. That means this should come down to here. Address register selects will be on the left there. And that's the height of our board set. Obviously width is yet to be determined. It does feel quite cramped though. I actually hope to fit it into a narrower board than this. But the big question there is more or less narrow. than having room for 12 of those. I'm going to attempt to fit all the circuitry into there, and I think that should go quite comfortably. Okay, let's get some chips in here and then see how it all fits together. May be able to organise it a bit smaller. Right, so we've got the incoming clock, but we want the inverted clock. We want the inverted clock to run the 138s, and we want a non-inverted clock to go to all the address registers. We also want an inverted copy of the incoming reset signal. The main reset line is active low, but then the clear that goes out to the address registers is active high. Now we've used 3 out of the 6 inverters on this chip, so the unused inputs, we need to bring those low. Okay, 1 chip down, many to go. Now, I did make one slightly worrying discovery when I was putting together the parts order for this. On the breadboard version, I've used 74LS139s to do a few jobs. And I don't seem to be able to get those in the surface mount HCT variety, but we can use a pair of 138s to do that. We just need to bring that third address line low. So these are the active low enables and this is the active high enable. So for this pair we just want to set them all to enable. That's 2 sets of output lines done. Let's look at the main bus control now. Okay, the low and high half of this pair differs in that we connect line 3 to an active low input here and the active high input here. Alright, awesome, that's the main bus assert line done. Now we need to do the load. Okay, line 8, which is the lowest of the high ones. For load, I don't have anything to put there. I'm trying to avoid having different things on the same address lines for load and assert. So if we really got tight, we could use that for loading something that didn't need an assert. But yeah, I'm inclined to skip that for now. Same with the 0. Actually, if we got really desperate, we could put ALU assert into the 0 position, because it doesn't matter if we're not doing a transfer, if we're asserting something. An assert is only a load, and then this would become a spare device line. Now this is the constant register load line to load from the bus that we've added to the header, but we don't actually have on our register at the moment, but that's there for future expansion. By future expansion, I of course mean that's what I'm thinking of doing if I don't run out of time. Same as before on this, but we do need to bring the clock line in for the load operations. Okay, so that's done. Apart from, I've got this membridge direction. Now, basically, this line we want to bring low whenever we're performing a write to memory. So this one is going to be merged with the clock, but this one we don't want to merge with the clock. What I'm about to do is going to feel very wasteful, but I actually think it's the most sensible way of doing this. Because if I put a 4-input NAND chip in here, then that's quite wasteful because I only need one of them. And it's also quite frustrating because that's a completely unique chip that I'm not using anywhere else that I would need to add to the bill of materials for this job. So because I'm already buying a stack load of these HTT138s, it's actually far easier for me to get the line just by doing that. So this is a 7.4 HTT138 being used as a 4-input NAND gate. That may be a little bit of a waste of its functionality, but there's every other option I've looked at would require me to add one chip to the build to get this line. And this is obviously elegant from the one perspective that it means I've just got another 138 rather than another unique chip going onto the board. Okay, so that's all the lines that go into the general purpose registers. Now we need to worry about the address registers. Right, the increments are another tricky one because I used a 139 on those, and that's the chip that we don't have. This felt really sensible when it was just half of a 74LS139. Doesn't seem quite so clever when we're using a whole 138 chip just for incrementing these two registers. But we can be highly confident that's going to work. If I was going to use a different chip for it, I'd want to order in the DIP versions and double check it on the breadboard. SP, SI and DI go on 1, 2 and 3 here. Okay, let's do transfer bus. Actually, I'll do address bus selection at the same time because it's almost identical. I'm trying to keep the indices of all of these on the demultiplexers the same, obviously matching what I've got in the program code that generates the control ROMs, so I don't have to update it all. Okay, so for transfer bus assert, entry 0 has ended up with nothing in it, and for address select, that's memory acknowledge, but in the exfer assert we've got this extra A mode one, which is a piece of functionality idea that I was going to look at in the future. But if I don't get around to that, forget I said anything. Alright, exfer load and deck. That's going to be a pair like we did for the main bus. I'm actually finding this enum at the top of my processor control binary program to be the best kind of source of information for what lines go where. So at the moment we're doing this. So we've got the transfer bus assert and we've got the decrements. I'd almost forgotten that I'd put the load constant from the memory data bus onto one of the lines here. Good thing I checked. I'm going to need some decoupling capacitors for all of these chips. 15 of them. My register boards, I put a single larger capacitor on for a bit more power balancing, but I think I'll stick 2 on here. It's a bigger board with more chips. Okay, famous last words, but I think that's the schematic done. That means everything here should be referenced twice. So on the PCB, it should be fairly clear if we've got stuff missing. Can worry about all these caps later. Actually had a bit of a rethink. Those two are going to be better off at the bottom, because that basically means the inputs are up the top and the outputs are at the bottom. Let's kind of be bold and assume we're going to be able to fit it into that space. It'll be much nicer. Visually it looks doable. Feels a bit cramped, but it should work. Appear to have lost a chip. Right, VCC is the top right on all of these, and apparently close to the VCC pin is the best place to put these. Previously I've put them at either end, but I'm always willing to accept a little bit of advice. Knew I had one more of those than I needed. Now, part of me refuses to believe the possibility that I could get a circuit like this working first try. But the majority of this is stuff we've tested on the breadboard, so it mostly is down to how much I've translated it correctly. So that, I think, is the one I deleted. I want to see what happens if I just run the auto router. Okay, so I spent a bunch of time yesterday evening trying to route this, and it's definitely struggling. But I've got a couple of ideas. Firstly, I'm going to expand the space out a little bit. It does end up generating a lot of vertical lines, and so I figure give it a little bit more room to work. Then the other thing is, I was trying to keep this nice and neat by putting the low and high portions of these pairs side by side. And of course what this actually means is that there's a lot of the lines going across ways, which gets in the way of the wires being routed vertically. So I'm going to see if I can actually try and put the chips that are mostly connected to the right hand side on the right, and the ones that are mostly on the left to the left. So these two have a lot of connections down to the outputs here, so I'm going to put those together. Okay, you can already see there's a lot less lines crossing the central point. Okay, now this configuration has given me a bit more success, so I'm going to tempt fate a little bit and modify it some. Can I save it? That's a good idea. I wasn't very happy with how tight I had to put these, and I've got more room now than I had before. Let's give that a go. Excellent, we've got a completed route. Now let's tidy it up a little bit. Now I do want to add a copper area here. I want a narrower snap than I've been working with. Okay, that doesn't look too bad. If I carry on like this, I might give people the false impression that I know what I'm doing. Okay, so here's the PCB. Looks quite nice. Now this is a companion to these PCBs. This is all carefully designed to mate up. These red ones are temporary. I keep saying it, but I'm planning to do a much larger back plane, but these will provide the hookups until everything else is finished and I'm ready to make that. I did notice that these holes don't seem perfectly aligned, or the holes seem aligned, but the pin headers don't seem perfectly aligned. Let's see what we can do. Okay, well that looks pretty good. It's definitely the most complicated PCB I've done, so I'm a little bit anxious to see it working. Okay, let's see what we got here. 74HCT138, need loads of those. 10 microfarad, 100 nanofarad, need one for each chip, and 74HCT04D, that will be the inverter chip. Do that one first. Have to remember these are rotated at 180 degrees compared to the others. With the first pins tacked on, it gets a lot easier. This technique of laying the solder along where it needs to be and then just kind of pushing it into the pins is working quite well for me. Let's have a closer look at all of these. Okay, let's get the passives done. I could tell that didn't feel quite right. It's just not making contact with the board there. I missed one. One thing to do is if you just go and melt the capacitor on the side where you originally anchored it, if you haven't got a good joint, it will move. So that one didn't have a good joint. I believe that is done. Now I think this video is going to end up long enough as it is once edited, so I'm not going to try and reassemble this into the main CPU build now, because I think getting that in and testing it thoroughly is going to be a video in its own right. But I very much hope you found this interesting. Thanks for watching. Goodbye.